Alpha from TwoSigma and George from Uber have been contributing actively to our Buildfarm effort that I just looked up on the agendas. We started talking about this in April, and somewhere in August, George particularly started committing large masses of code, 53 commits. Well, not masses, but for an open source project, it's great. And we've been meeting weekly with this group since April, and initially the core team members were George from Uber and Alpha, and also we've got Huawei contributors, as well as Twitter team was very interested in coming to the latest sessions. So welcome for you to join the session. This is a monthly working group where we're discussing the community efforts, and feel free to contribute. And at this point, it's also available for you to use, but George and Alpha will tell you all about that.
Hello, everyone. So my name is Alpha Lam. So today my topic, I'm going to go first. We'll go talk a little bit about the remote cache first, because that's one of the critical part that the remote X is going to base on. So so here's a little bit of disclaimer from our company. I have to give this because of our marketing team. So who am I? I work in a team called SDLC, Software Development Lifecycle for Platform Engineering for TwoSigma Investments. So we're based in New York. So our team's function is to manage the infrastructure for our build, test, and the artifact storage and the content distribution network for the artifact storage. So the artifacts. So I want to talk a little bit about our build and why do we use Bazel. So internally, we have a build system that's stitched together about 7,000 build modules. Each of them is a pretty bulky one. So and we practice like this mono-repo approach, which means every single push, we will build, test everything, right? So given we have 600 engineers around that number, we're doing about 5,000 full builds a day and about 500,000 module builds. And there's a lot of tests that we're running for every single push. So we're really hoping that moving to Bazel will speed this up. So we've successfully migrated a couple of the modules, about total 10,000 build actions to Bazel. We're actively trying to do this more. So what is our challenges when we move to Bazel, right? So first, we really need fast farm build, right? Like we have so many full builds a day, and each of the module builds can share code and a lot of duplication actions between them. So we want to be able to execute really fast and not waste any time of doing these things. And the users want to do really fast local builds as well. That means they go into work, they check out the code, then they build, and they, in a couple minutes, they should be able to see, and work from there. And so as the user can have multiple clones, so the same reason goes there. And we have a pretty resource-heavy of a test farm. We have a test farm about 6,000 cores, so it's really resource-heavy and time-consuming to run all those tests. So what is our solution to this problem? Our solution to this problem is to build a remote cache that is used to store the build artifacts and the test results. And the cache is, being remote means it can be shared between the build bots and the users. So like they would just share the build result, they execute and they go. So we contributed the first remote cache implementation to Bazel, and over time it has a lot of improvements made from contributors. Dan Fablik, he introduced the REST implementation. So Oof, who just talked here, he implemented the local disk cache and recently made it possible so that the remote cache works with sandboxing and other remote, other spawn strategies like worker strategy. So, and then of course there are many other contributors that I probably missed here. So thank you everyone for contributing to that. So what is it capable of in Bazel today about remote cache? So you can use it for build and test, and it will work for gen rule and skylock rules as long as they're hermetic. You don't tag them as local, as hermetic, then you can use it with the remote cache. So it can work with local sandbox execution. That means you run your job in the action in a sandbox, you fetch the results, and then you can share it with the other users. And theoretically, it can support any size of the artifact. So there's chunking support in the gRPC implementation, and then in the latest version of Bazel and master, it should support like arctext streams. So for REST implementation, it should support any size too. So from this point on, I'm gonna go dive deep a little bit about how this works as an intro for George. So how does Bazel execute? Everybody knows, I mean, most of you knows that Bazel is split into 3 phases. So loading phase, analysis phase. So after these 2 phases, at the end of it, during the execution phase, you have an action graph. And the action is actually what we call it spawns in Bazel. So in this example, you see about 3 spawns. So the first one is a spawn that compiles a code generator, and then the second one runs the code generator, spits out a header file, and then the third one takes in the header file, generator header file, compiles to it. So this is the same for build and test. So each of them, like Uwe just mentioned, each of the build and test action translate to just something called spawn. And so what goes into a spawn? So because we give Bazel really fine information about its dependencies, each spawn knows about what is the exact input and output files and the tools that are needed. And we know about the command line arguments and then the environment variables and other things such as the platform and what hardware it requires. Okay, and then we added something new to this picture called a spawn cache. A spawn cache has 3 functions. So first, it takes a spawn and computes it as a key, right? So we take the input files, compute a Merkle tree hash to it. We have a key, and then we add in the arguments, and then we add in the environment variables and a bunch of inputs to the spawn, and then we have a unique key to identify this spawn. And once we have this key, we can use this to store the result of the spawn, meaning that whether it compiles successfully, whether the test ran successfully, and then the list of output files that are associated with the spawn. And then we also, this spawn cache also has a content addressable store. So with the list of output files being hash keys or Merkle tree hash, you can go download the output files from the content addressable store. And we made changes to the spawn execution strategy so that before it go execute it, it computes the hash, look it up in a cache. If it is there, download the stuff. If it's not there, run it locally and uploads the results. That's how the remote cache works. So there are 3 backends for the remote cache today. So there are REST cache, like I mentioned earlier, like Dan Fablake implemented this. So there are 2 endpoints to the REST cache. So one, like I said earlier, one is the action cache, which tells you the results of action of a spawn, and then there's a content addressable endpoint, which goes to download the files in the directories. And you use it by the flag there. There's only 3 methods you need to implement. The head checks if the key is there. The get downloads the key, the put uploads the key. And then there's the gRPC implementation, which is a lot more performant and is being actively worked on. So you use it by the flag again, you point it to a gRPC endpoint, and it should go right like that. And lastly, there's a new experimental local disk cache implementation, which means you can switch between clones and point it to that flag, and they'll share the cache between the clones, between workspaces, of course. And so today I'm going to focus a little bit more about the REST cache. So in order to use it, you just need 2 flags, right? So and now I'm talking about in master. So in older versions, you don't have this flag, and just go to the master with this flag with experimental remote spawn cache equals to true, and then you pass in the endpoint of the REST cache, and you should be able to use it immediately. And like I said, it's the same goes for build and test. So here's a little bit of a benchmark taken from our build of how much speed up it can give us. So we take a build of a couple modules. They have about 10,000 build steps. Most of them are C compilation step and code generation step using Skylark and Gensure. And a local build using our 16-core machine would take about 10 minutes to do it. And with a cache build, mostly it's just downloading everything. Nothing has to be executed. It's about 30 seconds. So we expect that if you use a cache like that, will give you a magnitude or 2 magnitude of speed up. Okay. So I would like to share a little bit more about how we implemented a distributed remote cache inside TwoSigma. So in TwoSigma, we use Hazelcache pretty extensively. So Hazelcache is a distributed in-memory cache that's written in Java. And it's pretty easy to set up. So we combine it with Kubernetes. So It has built-in REST cache support, so you can just simply point Bazel at it, it'll run. So what about fault tolerance? Like I mentioned earlier, we use Kubernetes. So we use Kubernetes to set up, let's say for this example, a replication of 2 pods, and they form a memory cluster inside it. And then Kubernetes provides us the load balancer, so it'll switch between the 2, and the cache is switched and is replicated across 2 machines. And their LLU cache support by default. And it's pretty easy to monitor. We just put it in other JMX trends and send it to like statsd. And you can easily do this. It's easy to set up. There's no code at all. It'll give you fault tolerance and replication. That's pretty nice. So what are the best practices from what we learned from using the REST cache or remote cache in general? So first of all is to write pragmatic rules and try to use sandbox as much as possible. And I try to avoid using like absolute paths in your gen rule or your Skylab rule, right? Because across machines, those could be different, and you don't want them to be different because that gives you incorrect results in your executions. And and more importantly, if you have a farm of build bots, it's good to have them all using the same tool chain. So the way that we do that is by using containers in Kubernetes. So we ship our build bots in Kubernetes and make sure they all have the same bits on the disk. And lastly, one thing I mentioned is it's also good to try to check in your tool chains. For example, check in your JDK tool chain or even GCC or Clang to make sure that everybody has the same bits for them, and then you have a reliable cache. And then at the end, is try to avoid cache contamination, meaning that you have bad users that uploading bad stuff that points in everybody. That's something to prevent. The way that we do it today is not so nice. We have to explicitly disable that for the dev machines, but maybe in the future we can improve that. Okay.
I'll give you my patch.
It's cool. So here's a little bit of limitations about the REST cache implementation. There's no authentication, so it doesn't work with if you have Kerberos or other auth mechanism. There's no chunking. So give it a try on like uploading large files. If it doesn't work, file some issues. We'll work on it. And then there's a common issue about all these remote cache implementation is that you have to download all the intermediate artifacts. You have to execute it because that's the way currently it is implemented. So I want to talk a little bit about these limitations, and there's some potential improvements maybe we can do in the future. So here's a example that I mentioned earlier. So on the left, you have the code generator. You compile the code generator. And the second one, you run the code generator. And then the third one, you take the generator header and run the final binary. So the cache works by hashing the input of the command line and the content of the files of that direct input of that spawn. And because of that, we have to download the results from the previous spawns, or at least a manifest of it, to know the hash in order to compute the hash for the next action in order to download the results, right? And so that's why it eats up a lot of your network bandwidth. And it's of course wasteful. So one potential improvement in the future is that we could make the hash key transitive, meaning that the hash key for the first action can be used immediately for the next one. You don't have to download the results. And so with this, all you need is just to have the source files on disk, and you can have a whole Merkle tree graph of the entire action, and then you can pick anybody, any point in time, any point in the graph, and try to download the results and execute from there. So like I said, this is a potential improvements, and Oof told me this is going to be a really big change, but we'll see. So from this point on, I'm going to give it to George to talk a little bit more, a lot more actually, about remote execution. It's a pretty cool demo.
Thanks, Alpha. So before I even jump into my talk, I'll say that I've got a fairly large build running here. 100,000 actions spinning on my 8-core machine, and occupying fairly little memory, but doing fairly CPU-intensive things. I've got about 50,000 CPU seconds worth of computation to be done in this build, and I've been running it since the presentation has started. Keep in mind, we haven't even computed the right-hand side of that action count because we're still at 80,000. It'll eventually go to 100,000 or 99,000. Hi, I'm George. I'm from Uber. I am the lead build engineer for Uber ATG, the autonomous vehicles division of Uber. It's about all I can say about it. I've been a build system engineer for about 10 years. I've hopped around, done a bunch of different things, built a couple of my build systems myself. But where I come at this from is I'm a Linux systems programmer. I'm used to dealing with hardware. I'm used to dealing with bottlenecks that don't really get to be avoidable. You have to take shortcuts around everything, and that's what we're doing. We're trying to make the build system that you know and love, that you get exposed to every day, that all of your developers have to interface with, be able to utilize resources beyond just the crappy laptop that you gave them. The 8 cores that you gave them are never enough. The 64 cores on the big workstation machine are never enough. The 1 gig network that you built is never enough. And so we need to build something that's going to be usable at scale and at, I would say, if you can't even budget in many cases in terms of build systems going forward. This is just anecdotal stuff from me. I can't budget for the number of people that I expect to have, or the amount of lines of code that I expect to have, or the resources that I expect to support, or the number of different distributions or different tool chains with parallel executions that I intend to support, because everything is quadratic. So I have to leverage the only ability that I have to execute in quadratic frameworks, and that's to put more things in more racks and make them more accessible all the time. So that comes down to what Google has released as the version 1 test API for remote execution, which includes not just elements of remote caching and elements of content addressable storage, but also this little execution API. The execution API is the entrance into how we're going to distribute work over these clusters. And our lingua franca, our primitive of operation, is the action. I'm sorry, I didn't coordinate with Alpha before, but in his terminology, we have spawns. Spawns are actually instances of actions, or one way or another. In short, I'm gonna refer to these things as actions, and I hope that's going to be clear going forward. Our initial implementation, our reference implementation of what the Google team brought us in terms of the 3 core services has come out in a project called Buildfarm. I have a little link here to our open source project, and it lives under the Bazel community and theoretically is, a little bit sanctioned by you guys. Our architecture for Buildfarm models very closely to the API's definition. It is a services aggregator. You might also call it an instance multiplexer. And if the latter part of that is confusing to you, hopefully I'll get to it in the later sections of the slides. The main 3 services that we're supporting are, as Alpha mentioned, a content addressable storage, an action cache, and an execution service. The interface for the top 2 is very similar. The interface to the bottom is very different. And then the instances are ways that we divide the selectable pools that we want to access from the client, meaning if I want to access the high performance pool, or the memory pool, or the locally available pool, or the Euro pool, or the US pool, whatever we need to get access to, this is actually up to how people are doing the Buildfarm installations themselves. So our content addressable storage is used by both the execute framework and the action cache unit, and it's interfaced to the client for retrieving blobs. When I say a blob, I mean a bag of bytes, and that bag of bytes has a key in the content addressable storage system that is unique, hopefully, to the content that you're putting in, but more specifically is deterministic based on the content that lives in there. So your bag of bytes that you're storing for Hello World, the string, does not differ from anyone else's storage for it. It will always map to the same key. The key for this is the computed digest of those bytes, and the value is the mapping. I hope my crude little diagram has been efficient and illustrative in terms of what we have here. So you can only have keys that map to your specific values, which means you cannot associate knowns to unknowns. We can only find things that we know about and then be able to retrieve a larger representation of that. getting into what the execute system does and what the action cache system does, we have to get down to action definitions. Alpha's covered a lot of this. This is essentially required for remote caching. It represents the definition, meaning it is a message that describes the individual action or spawn that you're going to be performing. And it includes a Merkle tree of inputs. It includes the execution commands and the environment that you're required to get to the outputs that you want to get. And it says, here are the places in which I expect you to provide outputs, that is to say file names, not file contents, because we don't know about file contents at this point. But it expects to produce, A.O for compiling A.C, etc. So taking those action definitions, we get to use our action cache. This is different from the cache in really only one way, in that the key is not computed based on the value. The key is the digest of the action definition from the previous page, the spawn definition of what we actually want to store inside of the action graph. And what we retrieve out of that is a message that describes what that action did. So we're looking forward into the future and saying, based on having needed to do this action that was perfectly hermetically described with all its inputs enumerated and all the environment variables that it read on execution, here is the output of it, and here is where you can go get that. The action result includes a whole bunch of different things, specifically a list of all of the inputs that were specified and the way to get them and the keys that you can use to get them. So if we have action caches and we have action definitions, what we really want to do to get off of that laptop and off of that one machine or into the larger world of execution is an execution service. And an execution service is going to interact with a couple of different public APIs, most notably the Google Long-Running Operation API, and currently the Google Watcher API, although the Bazel guys keep telling me that they're going to cut that out. This is how we get from your action definition in the case where we have a miss in the action cache through to the action results. So this request is really simple, and in the spirit of the former illustrative diagrams, we have said the entry point is the execute action, and the result is the operation that you can then query to retrieve your action results, your action status, whether or not it completed successfully, and then this thing will actually upload into the action cache all on its own, as long as the right parameter was specified. So those are three things that are fairly intuitive. Instances get a little bit harder. And the reason I want to highlight them is because we've sort of ignored them in most of our talks, both within Google and without, where we know that people want to identify a set of resources, and we know that people want to change their behavior depending upon who is asking for what. But the instances are really the way to do that. So our Buildfarm endpoints, all three of them, CAS, execution and action cache, as well as all the subsidiary APIs that we're using, all know about these instances, and they're baked into the resource names or they're baked into the requests, and they allow you to do resource partitioning, which means saying that you, by requesting the pool high mem or high CPU or whatever, can go to the right set of resources for execution. And even better than that, as service installers, I know we're not DevOps people by any means, but sometimes it tends to come up that you need to know how machines talk to one another. You have the ability with instances to sort of transparently route requests to different resources. If you want your resource to be named local, then maybe it picks the right place. If you want your resource to be the some sort of a cascading set of hierarchy of resource accesses, that's what we're aiming for. It's funny that we bring up the local execution. We're actually preparing in many ways to live in a tiered world where we can go to a local thing that then proxies through to a remote, that then proxies through to production resources that are only accessible to CI machines, that sort of thing. The interactions between those are, as I've said, we've got the possibility of delegation. We've got the possibility of intermediate caching, which means we can sort of fan requests through on demand to intermediate levels and make sure that those propagate and get stored in some higher coherent to the execution or higher coherent to the client cache location. And then we've also got the ability to limit access levels, not just based on endpoint requesters, but also based on which instance you're requesting, having credentials that go into this service, and we are credentialed, even though I turned that off for the moment. Have that ability to specify access to this. One of the things I read in the original Big Table doc was the fact that the quotas weren't built in initially, and I sort of liked that because it felt like every other system that I had ever prototyped, and that we had to get somewhere in terms of trying to delineate not just access by resource specification, but also access by the qualifications of the client, and let us limit that up. So our reference implementation goal was simply to take the API that was given to me, given to all of us, and run it through a smoke test. We came up with some very small implementation detail issues that we wanted to bring up to the community, some small issues in Bazel. Those all got corrected. Thank you, guys. And then provide something really simple that can work and scale for execution. Our design is not complicated at all. If you go and take a look at the service online, you're going to see one layer for service, one layer for each one of these instances that gets provided, and a couple of other different sort of utility mechanisms for defining the abstraction layers that we want to access each one of the primitives that we interact with, meaning the cache, the action cache, and the execution worker. And then we define that core instance pattern so that if anybody wants to pick this up and write their own instance on top of Redis or Hazelcast or Memcached or whatever, I'm showing my age in terms of tools, I realize, but the results that we got out of this were pretty cool. We came up with an LRU cache that needed an expiration callback because I implemented the action cache and then the outstanding operations in terms of executions in terms of the cache storage. When the cache expired, that I wanted to kill it in the other mapping. We have an operation queue service, which was the bare bones of what I thought I needed to ship work off to a requesting worker. So a worker comes in, says, give me some work, here's my platform. The operation queue service responds to that with work. When he's done, he comes back and asks for it, or whenever he's able to retrieve more work, he does that. That means that I had to implement a reference worker. The only way in which this is referenced is that we have used the operation queue service, which is not a part of the remote execution API, but I encourage you to tell me that I'm crazy or tell me that I'm wrong in using this. And instances are not bound to this in terms of requiring the implementation of the worker exactly the way that I did. Maybe they want to implement it some other way. We do a platform-only match, which is not too exciting. I'm not great at bin packing. I hear some of you guys are, but we can match up in individual platforms based on any set of string-based parameters that you request in. If an action says it needs something, we find a worker that matches it. Otherwise, we hang. And the last thing was that was kind of cool was I implemented cancellations last week because I had a bunch of rogue jobs running on my my worker cluster. Had to kill those off, and to do it, I had to make a feature to do it.